So far, we've seen the most important, one of the most important constituents of our service model, and this was the transit relationship, which is one of the most dominant ways of connecting two ASs to one another. The other important type of business relationships that we are going to consider is the peer relationship. Let's just try to build an economic incentive of what we mean by a peer relationship and why we believe or why it is the case that certain ASs will enter into this type of relationships on the internet. So imagine that in this particular example, there is no direct link between AS1 and AS2, but there is a significant amount of traffic that AS1 needs to exchange with AS2, either because there are lots of hosts that produce traffic to one another, or these ASs have different customers, and these ASs are actually responsible for exchanging the traffic on behalf of their customers because they provide transit service to them. In both cases, or it can be any of these cases, it can be the mixture of all these cases, whatever happens here is that there will be a significant portion of traffic, even gigabit per second or terabit per second traffic, that will be exchanged between AS1 and AS2, and if there is no physical connectivity and routing level connectivity between these two autonomous systems, that the only way to exchange this traffic is through a transit provider, which is all nice and cool, because the transit relationship that these guys have in this simple setup will basically cover the exchange of these types of traffic. But the problem is that AS3, which happens to be just a common transit provider for AS1 and AS2, will charge both of its customer ASs, AS1 and AS2, for exchanging this traffic. And whenever this exchange traffic goes to the range of gigabit per second or even terabit per second that we've seen in the transit pricing example, that this can amount to even millions of dollars of transit fees that both of these customers will need to pay to the transit provider. So in this particular case, when there is significant amount of traffic to be exchanged between AS1 and AS2, then there is a very strong economic incentive to remove AS3 from the loop, the transit provider from the loop, by establishing a direct physical link between AS1 and AS2 and start to exchange traffic directly between these two ASs. And what happens here is that this traffic exchange will basically not charged by any of the actors here. This is basically means a settlement-free peering relationship between two ASs. So again, the economic incentive is that whenever there is significant amount of traffic to be exchanged between two ASs, then if there is no peer link between the two ASs, then the only way to exchange the traffic is through a transit provider. But this will actually involve lots of transit fees, and to actually just remove the intermediary from the picture, we can actually just get this physical relationship between the two ASs and start to exchange traffic. What happens here is that the AS1 and AS2 will connect their networks physically and then enter into a so-called settlement-free peering relationship. So this is the other type of business relationship that we are going to consider. The first one was the transit relationship, and the second one is the peering relationship. Now, in order to differentiate between the two, we're going to just use a single line segment to connect AS1 and AS2 in our schematic diagram, but this particular line segment will not have an arrowhead on it, which will essentially just indicate this idea that there is no cash flow in this peering relationship, because this is essentially settlement free. Both AS1 and AS2 are equally interested in maintaining this connectivity and will not charge the other one for these types of traffic exchanges. While this is sort of a master-slave relationship between a provider and the customer. A peering relationship is much more of a horizontal type of relationship, which basically connects two ASs of equal size or equal importance instead of connecting a smaller AS to a larger AS. Again, let's just run to Dr. Peering for a nice definition. Dr. Peering says that an internet peering is the business relationship whereby two ASs reciprocally provide access to each other's customers, and there is no cash flow involved in this process. What's very important here is that a peer relationship is always a bilateral relationship between two ASs, so it covers exactly two ASs. In this particular case, it is AS6 and AS7, and it essentially covers all the traffic that flows between AS6 and AS7. The simple idea to understand that if we hadn't had this business peer relationship here, then this traffic would flow through transit, and this would incur additional transit fees. But whenever there is a peer relationship, we can just basically short circuit these types of transit traffic and save a lot of transit fee on that. And the forwarded traffic essentially covers any traffic that would otherwise be exchanged between AS6 and AS7. So basically the traffic between each other and between all of their customers. This also means that the customer of their customer is also covered with this traffic exchange, but we are going to just go into that in the next lecture. So peering considerations. The peering essentially comes for free. Of course, operating the direct link costs money, but whenever the transit fee that we can save by not going through an intermediary is larger than the operating fees or operating expenses of maintaining the direct link, then there is a very strong economic incentive to establish a settlement-free peering relationship. And this means that there are lots of peering relationships that going on the internet, but still we do not have all the ASs to form a peer link between one another. There are two reasons for that. One is that whenever the mutual traffic exchange between two ASs, either because the ASs are very small or they are located at very distinct and distant geographic locations. So wherever there is not significant traffic between two ASs, there is no economic incentive to actually maintain the direct link and pay the peering links costs. In this case, there will not be peering relationships. The other important cause that might preclude one AS to go into a peering relationship with another one is that a larger AS will never or typically not peer with a smaller one. Okay, because this way, basically a larger AS could also provide a transit service to the smaller one and could collect monthly fee. Why would it actually just change or jump from that profitable status quo to another one wherever it just basically exchanges traffic for free? This is not something that on such a competitive market, the internet service provisioning market is. This is something which would be allowed in this setup. So there is a very deliberate and very detailed and sophisticated planning that will govern the types of peering relationships that are created on the internet. We don't know too much about these types of considerations, and at the moment we do not even have good economical models to reason about the way these markets actually work. But one thing that we definitely know is that there are a couple of ASs which publish the types of policies that govern or that actually govern the way they form their peering relationships, and from these published data we can distinguish between two different peering policies. So again, a peering policy, so whenever we have the AS typically declares the conditions under which it is willing to enter into a peering relationship with another AS. Okay, the peering policy is basically something, the set of rules that an AS uses to choose the ASs with which it might go into a peering relationship. There are two typical examples of peering policies. One is selective peering. This is typically the type of peering policy that is used by internet service providers, in which case there is a very strict peering policy. There is a very strict set of criteria that the other AS must fulfill for our AS to enter into a peering relationship with that other AS. The typical types of criteria that the other AS will need to fulfill is that, for instance, the customer cones must be roughly the same size. Again, whenever we talk about AS size, we mean by that the number of, as we introduced in the beginning of this lecture, is basically the number of AS, IP addresses, and the size of the IP prefix that is announced by the AS into the inter-domain routing system. So whenever the customer cones of two ASs are roughly the same, then this will be a good candidate for a peering relationship. There must be significant and symmetric traffic demands. So it does not go that one of the ASs generates much more traffic than the other way around, because that would be an indication of an asymmetric relationship between two ASs, and that would bring the larger party towards a transit relationship instead of a peering relationship. So there must be symmetric traffic demands, and usually they actually monitor and measure traffic, and whenever the symmetry goes away, the peering policy might be terminated. A third criterion is that we want the other AS to have multiple geographically diverse POPs. So a typical example in the United States is that that it is required that the two autonomous systems can establish peering relationships at multiple locations inside the US, for instance, one in the East Coast and one in the West Coast, which has all sorts of important traffic optimization and routing optimization consequences. We are going to just see that a couple of lectures later when we discuss hot potato and cold potato routing. Finally, usually a selective peering policy will require the other AS to maintain 25 hour per each weekday support. So wherever there is some problem with the peering relationship, there is something we can call on the other side and ask support from. So this is selective peering. This is a very strict set of criteria which chooses the types, the ASs with which we can establish a peering relationship. The other type of peering policy is called the open peering. There is no criteria. So an open peering policy says that an AS is willing to go into a peering relationship with any other ASs. We are going to see in a couple of labs later in the internet monitoring lab that there is a very nice resource, the peering database, which collects the peering policies of different ASs, and there are lots of interesting examples there for selective peering policies and open peering policies. Here is an example. We won't go into too much detail. This is the peering database entries for Facebook and for Google, and as you can see, this is the peering policies for Facebook, and Facebook openly declares that their peering policy is selective, so they will not go into peering relationship with anyone. This is in contrast to Google, which declares an open peering policy. Google will basically enter into a peering relationship with anyone on Earth, and there is a very important and very good economic incentive to do that, because Google is typically a huge transit content provider. So anything it can just save on transit fees will just improve its profitability. Peering wars is this is the collective name of all these different tussles and fights that can happen between between different ASs whenever it must be decided whether or not to create a peering relationship. There are lots of good incentives to create a peering relationship, like it might decrease transit costs, and it might also decrease the latency, because by removing the intermediary, we can directly exchange traffic with the peer AS. But of course, on the other way around, there are very strong incentives to not go into a peering relationship, because this can be a potential profit loss compared to the case if we provided transit to the other AS. This is by far the most contentious policy issue in today's internet. An important definition that we should be familiar with in the context of peering relationships is the notion of the institutions that are called the IXPs. IXPs are dedicated infrastructure that is maintained and operated just for the purpose of ASs to establish peering relationships with one another in mass. So this is basically an internet exchange point. An IXP is a special network infrastructure. It is dedicated to allow ASs to enter into peering relationships easily. And easily is very important here. We're going to just see how important it is for an IXP to create the most simple onboarding experience to the ASs. It provides peering services too. The IXP is typically a well-connected data center where ISPs can just bring their routers. They can bring their POPs there. Recall that a POP, the point of presence, is basically the set of network devices, in this case IP routers, that an ISP operates at a certain geographic location. In this particular example, the geographic location is the IXP's data center, so the ISPs just bring their routers there, and whenever they have a router at an IXP and they have a link, or they actually have a port to the IXP's infrastructure, from that point, it is basically free to create new peering relationships with all the other ISPs that also have POPs at the particular physical location and the particular IXP. So in this case, the IXP essentially ensures that any two member ASs can connect via their POPs, and wherever we actually just put just one POP to an internet exchange data center, from that point there is very little additional price of establishing new business relationship. So what we can exploit here is the mass effect. So whenever an ISP appears at an IXP, it pays an initial cost that will be basically the cost of locating its POP at the IXP's data center. But from that point, it is very cheap to establish new peering relationships. How do we envision an IXP? This is basically the most typical example is an Ethernet interconnect. So there is a very high capacity layer 2 Internet interconnect, which provides access to any two ISPs through this shared medium. The ISPs and the POPs actually just pay a monthly fee based on the ports and the port speeds that it have, that they lease to this ISP to connect to this IXP Ethernet interconnect. And this interconnect makes it possible to create arbitrary peering relationships like ISP1 and ISP3, and ISP1, ISP4 will be a peering relationship, but it is not mandatory to provide the peering relationships with all the POPs that exist here. So the ISP might just choose to not enter into a peering relationship with the ISP2, and this is within its own decision and autonomous decision to actually create the types of peering relationships that it wants to just maintain in an IXP's topology. So IXP's goal is to attract as many ISPs as possible into its data center, because the more ISPs are there, the larger incentives there are to new ISPs to just create POPs in the IXP, because then they have an access to a larger base of ISPs. Member ISPs are charged on a per port basis, and in the United States we see for-profit IXPs, while in Europe and the rest of the world we usually see non-profit IXPs, which just use their profit to actually just build their own infrastructure and develop their own infrastructure. A couple of examples of IXPs. An IXP may connect hundreds of ASs. The transit rate can match that of the largest internet service providers. The largest IXP as of now is DECIX, which is the German IXP. DECIX operates data centers at multiple locations inside Germany, Frankfurt, Hamburg, and Munich. But also they now are expanding into global operations. As far as I remember, they also have data centers in Hong Kong. Couple of hundred ISPs, more than 5 terabit per second average rate, and this is not even fresh data, so we might see much larger traffic rates these days. We also have other examples in Europe. The Amsterdam Internet Exchange and the London Internet Exchange are also two non-profit IXP operations. The American market is basically dominated by Equinix, which is a for-profit enterprise that operates IXPs at basically all the larger cities around the United States and provides IXP services for profit there. There is also an internet exchange in Budapest. It is called the BIX, the Budapest Internet Exchange. It's of course not that of an important player, but it basically connects and collects all the autonomous systems of the Hungarian internet market at a single place. And we are going to just see in an example where this makes a lot of sense. Just a short note: we've seen earlier this notion of the stub AS, but we haven't really defined this notion yet. So the idea here is that a stub AS is an AS which does not provide transit services to any other ASs in the internet. So it's basically just an AS that hangs as a leaf node on the internet topology, and it just basically just consumes and generates traffic, but does not provide transit services. Roughly two-thirds, half or two-thirds of the autonomous systems connected to the internet are today stubs. The rest, of course, are transit ASs. These are the non-stub ASs. Let's see a particular example. This is the Hungarian academic backbone, the H-bone, which is an autonomous system identified by the autonomous system number 1955. Like being an academic backbone, this is a government-operated infrastructure. Customers of H-bone are the government network, the network of elementary schools and secondary schools, and of course all bigger universities in Hungary are also providers, are customers of H-bone. We have BME, for instance, here. So these are basically just the ASs that serve as the customers of H-bone. Of course, H-bone does not charge BME for this transit service, because of course this is also covered by the government. The important observation here is that H-bone essentially peers with all the rest of the Hungarian internet. All the Hungarian ISPs are some way or another peers of H-bone, which makes it possible to exchange all the local traffic in the internet without actually paying transit fees to any of the transport providers of H-bone, like Géant, Telia, and Cogent. So as long as traffic is exchanged from one university to any of the Hungarian operated ISPs, this will be terminated, and this will remain inside Hungary, and this makes it possible to save transit fees. So basically that's all about the service model, the transit model, and the peer AS-AS relationship, and then we are going to just jump on the second important topic of this day, which is the AS hierarchy.